Yesterday we covered the first two tests of the semester. Um, Remind you of what we had covered early on, and of course some of it, the derivatives, we used quite a bit throughout the semester. We'll start with test 3 today, and well, somebody made the comment you didn't eliminate very much. Well, first off, we're going to eliminate a couple problems out of test 3. There will be no linear approximation or approximating using Newton's method. Yes, approximating a solution. Those types of problems are good for computer programs, but we have to be aware that there is that possibility if we end up in that field and doing computers. But this is problems 1 and 2 out of test 3. Nothing like that will be on the final. So, good start on what not to expect, but now we're back to what to expect. And, well, the next 3 problems are applications. You can expect at least some applications. I'm not going to give you one of every application we had on the tests, or that would be the entire final if I did that, but probably 1 or 2 of these, 3, 4, and 5. 3 and 4 deal with the maximums and minimums, and 5 deals with related rates. So you can expect at least one like that. And then the rest of the test was a lot of the major concepts that come out of Chapter 3. Maximums, minimums, increasing, decreasing, concavity, so you can kind of expect at least something dealing with those topics. Maximums and minimums, what can we say about those? Okay. Typically where the derivative equals 0, one other possibility would be where the derivative is undefined. Critical points, find critical points and then see whether they are maximums or minimums. Critical points could possibly be neither as well, so we've got to check that out. Finding maximums and minimums. Increasing and decreasing, what can we say about that? Increasing is where what? Okay, first derivative is positive. Decreasing is where first derivative is negative. And then concavity. Concave up would be what? Second derivative is positive, okay, and then concave down, second derivative would be negative. And then what do we call the point where it changes concavity? Okay, inflection point. Where do inflection points occur? Second derivative equals 0, okay, or at least a possibility. Sometimes second derivative equals 0, but yet we don't have a change in concavity. But if there is a change in concavity, it will occur where second derivative is 0 or where it's undefined. That one's rare, but that is a possibility. So lots and lots of things with first and second derivatives. I think you guys had that down pretty good, but definitely go back and review on that. We did look at a problem based on the graph of f primed, but for the final, nothing like that. Nothing like number 10 on test 3. Given the graph of f primed, what can we say about increasing or decreasing, that kind of stuff. So don't worry about that one. However, problem 11, sketch the graph of a function that satisfies the following conditions. Definitely a possibility there. I think back in test 1 maybe we had another problem similar to that. Given certain conditions, sketch a graph that fits that. But definitely with the first derivative and second derivative, those types of problems, there will be more than one correct answer. In fact, there's an infinite number of correct answers, but all will have these same characteristics. It's kind of the rest of the graph could be different based on what you identify, but certain conditions must be satisfied. And typically you get, probably most of you will come up with the same graph anyway, but so definitely something like that. And then 12 and 13 will be a yes on that. And these were finding vertical and horizontal asymptotes.
You said yes, like it's on there?
Yes, it is a possibility for these to be on there.
Oh, possibility.
So. Now, we also, through the unit, we also looked at graphing, physically plotting out points and graphing. There won't be anything like that on the final. And we did some oblique asymptotes in class, but there won't be anything like that on the final. It's something good to know, but not something you absolutely have to know for the final. So test 3, basically everything except for problems 1, 2, and 10. Does that help at least to eliminate some things? Test 4, which hopefully is still somewhat fresh in your mind. Working with antiderivatives or indefinite integrals, and then later on the definite integrals, where we're able to use the antiderivative to calculate the definite integral values. Test 4, lots of integral, find the integral, calculate, evaluate, however you want to say it. 1 through 6, find your antiderivative or indefinite integral. Now, those know your integration rules. Okay, again, the shortcuts there. Trig functions as well. Just got to think backwards from the derivatives. I always have to take a derivative before I can take the antiderivative, especially those trig functions. And then one major operation for integration is substitution. Let u equal something and then du, get that completely changed into terms of u, and then usually it's a lot easier to find or actually you're able to find the antiderivative in terms of u. So lots of those types of problems. Now, problem number 7 is solving a differential equation, and we're not going to worry about that for the final. And those problems showed up elsewhere as well, but we're just going to skip over that. You'll have an entire semester of solving differential equations after Calc 3. I know you're probably really excited to get to that point. Or some of you maybe get away from this stuff. 8 and 9 will be, yes, a possibility for the final. Approximate area using rectangles. And probably I'll stick with 4 rectangles. So instead of 8 or 16, or I want to make sure you're able to get the test done Wednesday. So. And either right or left endpoints. Okay. Use the height represented by the function value at the right endpoint, or the height with using the left endpoint in the function value. Okay, so rectangles, left endpoints, right endpoints, just like problems 8 and 9. As we work through that generally, we led up to the definition of the definite integral. I know some of you will be disappointed here, but no definition of the definite integral.
Dang it. Good mood today compared to.
Now, we are going to probably have a definition of the derivative, but I will at least limit it to just that. No definition of the definite integral. So don't worry about number 10. Also, we can eliminate number 11, kind of the first fundamental theorem of calculus. Given a function in terms what looks like a definite integral, finding the derivative of that. We're not going to have something like that. But the second fundamental theorem of calculus is basically what we use for the rest of the, well, yeah, from 12 on. So, definitely be able to evaluate a definite integral. And that, again, in general, the second fundamental theorem, if little f is our function, then capital F is going to be the antiderivative, or at least an antiderivative, and we evaluate the antiderivative at b, then subtract the evaluation of the antiderivative at a. Few of you are getting that turned around with f of a minus f of b, but it's the f of the top minus f of the bottom. And some of those are just straightforward antiderivatives. A few of them you had to use substitution. So integrating using substitution is very important, and you'll need to be able to do that. And we did introduce area under a curve over a certain interval. And then this last chapter, we took that even farther. But find the area under some given function above some interval on the x-axis. Now, I will say there's nothing like number 20, where given a graph and then integrate based on that graph. But the integral given a formula, an equation for a function, definitely find the area of that region. Okay. So for test 4, everything except 7, 10, 11, and 20. And hopefully test 5 is real fresh in your mind. Definitely possibilities with acceleration, velocity, position. Whether it's like the first page of problems with some vehicle driving down the road and applying the brakes, decelerating. If we're decelerating, make sure acceleration function is negative. Okay. Or perhaps vertical motion, like problems 4, 5, and 6. Now, once again, there's a solve the differential equation. That will not be on the test, on the final, so I guess we should say no. What in the world, I guess. No number 3, but pretty much the rest of chapter 5 is possibility. But really it's, very general. Got your acceleration, find the velocity, find the position, answer the questions based on what particular knowledge we know. And then the last 6 problems, guess what? Find the area. Find area of this bounded region between 2 curves, or however it's described.
That's gonna be on the test. It's only half of our test.
Yeah, so probably at least one like that, maybe even more, but the applications of your definite integral area is definitely an important part of that. So, but that's pretty well. The area of a bounded region could be described y equals some function of x, or perhaps x equals some function of y, and maybe between x equals y squared minus 5y plus 6 and the y-axis, or that is a possibility where it's all in terms of y instead of x. Some of you struggled with that a little bit on the test, but most of you are able to kind of think rotated. So that is what to expect on the final. So any particular problems that you want to see? Okay, we're to find the area between this curve and the x-axis from x equals 1 to x equals 2. This again from test 5, problem number 10. How would we set that up? Okay, that definite integral from 1 to 2, and then the function. Okay. Now, this one, the more complicated thing is how do you do the integral, find the antiderivative, and that is more of a substitution problem. Looking at this, we're going to let u equal what? Okay, there's a couple different choices, but the easiest one would be all on the inside of the radical. Let u equal 3x squared plus 1. And then du, take the derivative. Du is going to be 6x, and then dx. Notation-wise, it's not du by dx, but the differential notation. Now, when we think about this, we're looking at this and going to substitute, change everything in terms of u. This is already going to be represented by u, square root of u. What does the dx equal? Well, from this we can say dx is equal to, need to divide by 6x. Okay, and we can substitute that in here. Now the videos, Professor Berger shows this slightly different. Doesn't matter which way you look at it, both ways work. To me, going ahead and solving explicitly for dx, some students find that a lot easier than how he explained the problem. So we'll have the 2x square root of u, and then our dx becoming du over 6x. Now notice I did not put in the integral limits because once we do this, we're now in terms of u. 1 to 2 represents the x values. Okay? And there's a couple different ways to proceed once we get back to the definite integral. But for now, with the substitution, well, this needs to be gone, and with the du, with the x down here, those will cancel, so we're left with just terms of u. Now we also have the 2 in the numerator, 6 in the denominator, so we can say 1/3 on that, 2 over 6 or 1/3. And with the x's canceling, we're left with just square root of u du. Or we need to change that to u to the half du to be able to integrate. Okay? Questions up to that point? Now the antiderivative of u to the half, some of you are getting a little confused on that as well. We're mixing our integration and derivative rules. That's not good. We need to use integration or antiderivative rules, which is u to the half plus 1 divided by the same thing. We're adding 1 to our exponent instead of subtracting 1. Or we're dividing by that instead of multiplying by that. Derivatives we multiply by the power. Antiderivatives we divide by that power plus 1. Okay. So we end up with 1/3 times, well, we're dividing by 3/2, so we can invert and multiply. And then, again, this is still just in terms of u. So we get 2/9 times u to the 3/2. Now, at this point, we're going to be able to do a couple different things. One thing, we could have done this from the beginning. This is in terms of x. If we choose to leave it in terms of u once we do the substitution, we need to change our integral limits. If x is 1, u is going to be what? Okay, u would be 4. So our integral limits, we can change that to terms of u. We go from 4 up to, well, if x is 2, u is what? 13. So at that point, we could integrate from 4 to 13 in terms of u, and this is where the slight difference would be. Leaving it in terms of u would be evaluating from 4 to 13. Okay. So top of the next page, we'll finish this out and then look at the other slight difference in evaluating this. So we'll have our 2/9 u to the 3/2 from 4 to 13. Fundamental theorem of calculus. We can leave the 2/9 out in front. We'd have 13 to the 3/2 minus 4 to the 3/2. And then at this point, if we can simplify something, do that. 13 to the 3/2, there's not really any nice way to write that. You might think 3/2. Well, let's look at it in terms of the 4 first. That simplifies. The half power would be the square root. And then we take the square root of the number and then cube it. Well, we could either cube the number first and then take the square root, or it's easier to take the square root first, then cube it. Square root of 4 is 2. 2 cubed is 8. So this value would simplify to 8. But what we would get here is just the square root of 13 cubed, and that's not going to simplify. Well, one way we could simplify, at least a little bit, because we're cubing it. Okay, the square root simplifying could rewrite it as 13 times the square root of 13. I'm pretty flexible with how you write that number. Some of you just ended up writing out the decimal value approximation, which is fine. Okay. Now, if you do not want to change your integral limits to terms of u, what we would have to do at this point, we would go back to terms of x. And u, remember what u was? U was 3x squared plus 1. And then, since we're back to terms of x, we can integrate with respect to x. Our integration limits were from 1 to 2. So now, kind of the other direction, some of you like using the u, some of you like going back to x. Doesn't really matter. Both ways we'll find we end up with the same thing. Plug 2 in for x, what do we get? Okay, we get 13 to the 3/2. Plug 1 in for x, and what do we get? So again, this point we get exactly the same thing, just a little different route getting there. Pick the way that works best for you. Okay? So And the numerical value there was about, 8.638. So that's how that one works. Any questions there? There's the button I wanted to push. So test 3, number 3, good application here, one of the maximize or minimize. And the whole idea will have some sort of description of the problem. In this case, it's more of a geometry problem. Rancher wants to fence in a rectangular field. So hopefully immediately think rectangle. And then divide it in half with a fence parallel to one of the sides of the rectangle. So split it in half, draw another line there, and we're going to have two different pastures, two different areas, okay? But the dimensions here, dimensions of a rectangle, we'll call this the length and this the width. Now, when we're dealing with rectangles, there's two basic types of problems that we look at. Either area or perimeter. Okay. Area would be how big, well, this problem going on, it says, if 3,000 feet of fence is available for use, what are the dimensions of the rectangle to maximize the area enclosed by the fence? So in this case, we're wanting to maximize the area. So we've got to find a way to represent the area. Area of a rectangle is length times width. But to maximize it, we need to represent the area as a function of just one variable. So what we have to do there, do we know anything that relates length and width? Well, what's the other information given to us? Okay, 3,000 feet of fence available. And that's kind of like the perimeter. Now, it's not necessarily exactly the perimeter. Perimeter means the length around the outside. We have to make an adjustment on this because we're wanting more than just the outside. We're wanting this fence down the middle as well. So what I'll call the perimeter formula, perimeter equation, will be adjusted a little bit because of this right here. But we can say the 3,000 is going to equal what? Okay, right. We have two lengths and then 1, 2, 3 widths. So that gives us a relationship between the length and the width. And we basically just need to solve this equation for one of the variables and then plug it back into our function, our equation that we want to turn into a function with just one variable. Well, sometimes it won't matter which variable we solve for. Sometimes it'll be a little easier to solve for one than the other. In this case, it's probably going to be easier to solve for L. Okay. So 3,000 minus 3W equals 2L. So divide by 2 or multiply by 1/2. We'd get 1,500 minus 3/2 W. It's going to equal L. Plug that into the area, and by doing that, we now have area as a function of our variable w. So we usually see f of x as function notation. Well, here we can write a of w, and that's going to be 1,500 minus 3/2 w times w. Length times width is now a function in the one variable w. And I would suggest going ahead and multiplying through so our function is a little bit easier to work with. Once we get the function, now from here we'll just kind of talk through the rest of it. Once we get the function, what do we need to do with it? Okay, take the derivative and set the derivative equal to 0. Solve for w then, and that will give us the width. That gives us one of the variables for maximizing our area. Okay, and then from there, also need to find the length. Sometimes the question is, what is the maximum area? So find your width, find your length, and then calculate the area. So that all depends on the details of the problem, but up to that point, same basic operations to get there. Okay? Questions? All right, that'll do it for, I guess that's the last class period. Next time I see you will be Wednesday at 10:30, except you, and we'll get that final taken.